Hello, I'm Lorenzo Vigna. I'm a PhD student at Politecnico di Torino, and I will now present our work on the effect of impact velocity and friction on the in-plane crashworthiness of composite plates that comes from a collaboration between Politecnico di Torino, represented here by me, Professor Belingardi and Professor Paolino, and Instron, which is represented here by Andrea Calzolari and Giuseppe Galizia. After a short introduction on the crashworthiness of composite materials, I will present the fixture that we designed to test the crashworthiness of composite plates, the aims of the test performed in this research, and the result analysis. It's well known, both in the literature and in the industrial world, that composite materials are extremely effective in absorbing kinetic energy during crashes, because of a combination of high energy absorption and low weight. But today there are some criticalities that are making the research still ongoing. To make some examples, the difficult prediction of the behavior of the structure during crash, the expensive destructive testing of prototypes required to design this kind of structure following a trial and error approach, and the absence of a complete standard for coupon crash testing. In our research, we are working on a procedure for crashing flat composite coupons in impact conditions, in order to find the specific energy absorption and other properties of the material, useful for composite crash structure design and simulation. In literature, you can find several examples of fixtures specifically designed to crash flat composite coupons, applying an in-plane load. Here you can see some examples. Between the advantages of testing a flat specimen, we can find the absence of effects due to the specimen geometry and the low cost and easy manufacturing of the specimens. But we have, on the other hand, some shortcomings. A fixture is required to avoid the buckling of the flat plate, and it can affect the results because of the constraint condition given to the specimen. Here you can see the anti-buckling fixture used in this research. It can perform quasi-static and dynamic tests in impact conditions by means of a drop weight testing system. It can test specimens with different thicknesses and control the friction between the specimen and the guiding columns. Fastening these screws with different torques, it is possible to control the clamping force applied to the specimen and consequently the friction force due to the sliding contact between the specimen and the guiding columns. The specimen has a rectangular shape and requires a sawteeth geometry acting as a failure trigger in its lower part. The load is applied as a dropped mass getting in contact with the top surface of the specimen. Here you can see an high-speed video of the impact test. The failure takes place in the lower part of the specimen, while the load is applied in the upper part as a falling weight. The data that we acquire is a time force curve like this one that we see here. After the crash test, we can recognize the delamination as the main failure mechanism, with the specimen divided in two large fronts. To calculate the specific energy absorption of the material, which is the main result that we are looking for, we use the central part of the crash curve, because here we have the stable crash conditions. Here you can see the comparison between three different curves acquired on the same material and in the same testing conditions. The curves start with a smooth load increase due to the trigger. After we find a force peak corresponding to the transition between the trigger and the full specimen. Then we have a stable crash condition that gives a quite constant force. As you can see, despite the same material and the same testing conditions, results are quite scattered, probably because of the intrinsic variabilities of the mechanical properties, due to the material and to manufacturing effects. Going now a bit more in details in this research, the parameters that we wanted to investigate are the impact velocity and the clamping force. because we wanted to discover if there is a strain rate effect or an effect of the friction force due to the sliding between specimen and supporting columns on the specific energy absorption measured. For this reason, we designed an experiment with 5 treatments and the testing parameters that you can see here. All the tests were performed with the same impact energy. That means that to change the impact velocity, we changed the mass dropped by this instrument. The tests are performed at room temperature, and 3 repetitions are performed for each treatment. And now the main results. In these plots, you can see the effect of the impact velocity and of the clamping force on the specific energy absorption of the carbon fiber laminate tested. As you can see, both from the plots and from the statistics, it seems that none of the investigated parameters has an effect on the result. Focusing on the fractures after the removal of the specimen from the testing fixture, we see 2 kinds of behavior. Sometimes we find a strong elastic return of the 2 fronts, like in the specimen on the left, and sometimes we see that the fronts are permanently deformed, like in the specimen on the right. Sometimes the 2 different behaviors are also visible on the same specimen. In this example, we have a first layer that seems to have an elastic behavior and doesn't seem permanently deformed. The second layer, instead, is fully fractured and has a different deformed shape. On the other front, both layers are equally fractured and permanently deformed. Seeing the different failure modes observed in the specimens, we tried to understand if the failure mode was another possible parameter of influence on the specific energy absorption of the material. To understand this, a quantitative representation of the failure mode was necessary in order to find a possible correlation with the specific energy absorption. To have a kind of measurement of the failure mode and of the deformation of the specimen, we decided to measure the fracture angle, which is the angle between the 2 fronts of the specimen after the removal from the testing fixture, as you can see in this picture. Then, plotting the specific energy absorption as a function of the fracture angle, we found a good linear correlation between the 2. This indicates an influence of the failure mode on the specific energy absorption. The higher the fracture angle, the higher the permanent deformation of the specimen, the higher the specific energy absorption of the material. Then we tried to understand if it's possible to hide the effect of the failure mode to reveal the effect of the other testing conditions. To do this, we used the linear correlation between fracture angle and specific energy absorption to transform and correct the values, moving to an hypothetical condition where all the specimens have the same fracture angle of 120 degrees. So the specific energy absorption is increased for low values of fracture angles and decreased for high values of fracture angle. Applying this kind of correction, we see the results changing in this way. The impact velocity is not influenced, while the clamping force causes higher values of specific energy absorption of the material. This is due to the friction force that absorbs a part of the impact energy that is not negligible. In this research, we studied the effect of impact velocity and friction on the specific energy absorption of a carbon fiber laminate. We found that a third factor, the angle between the fronts of the specimen after its failure, significantly influences the specific energy absorption. Considering this effect, we found a significant increase of the energy absorption in tests with higher friction levels, and that no strain rate effect is visible in the range of impact velocities that we considered. Further work will be aimed at reducing the effect of the friction caused by the anti-buckling device on the test results, understanding the causes of different failure modes, testing different materials, and trying to use the test results to tune the material cards of finite element softwares. And that's all from my side. Thank you for listening and see you soon in Turin.